I'm sorry. My live was ended by some glitch on YouTube, but we're back. Can people please join here? An extremely sad occurrence has happened where my live was killed by a glitch. I am back. Thank you so much for being here and liking the live. I'll try retyping this because it's interesting. Hello, my music. Did you know if we took all the planets in our solar system and placed them end to end, starting at Earth, it wouldn't reach the moon? I guess that, I don't know. I didn't know that. Maybe that's true, yeah. An Android phone? Are you serious? No way. All of my devices are Apple at this point. It's not my phone. I think it's a glitch on YouTube. It's a glitch. It's a glitch. It's a glitch. It's a glitch. Now I have to tell everybody all of the things. It's 100% true. Pretty amazing stuff. That's so cool. That is really cool to think of, actually. Hello, everybody. Thank you so much for joining. Again, here on my live. The earlier version died, but here we are. Can we get 10 likes? Thank you so much. Oh no. Thank you, Jake. Jake is saying I'm very proud of you. Thank you. Hi, Daniel. Excuse me? There. I'll share the live and do all that stuff again. Hello, Eddie. Hello, J-Dub. Hello, Slayu. Slayum. Hello, Slayum. Ooh, we got 10 likes. Can we get 20 likes? I'm gonna make a new goal. This will be for all the colors. All colors of super chats. J. Manuel. Manuel has sent us a thumbs up. Manuel. Oh God. Hi, Benito. Manuel, thank you. Thank you, thank you, thank you. I was about to read the top fans on the other live and it died. It went away. Hi, Chiron. What's up, Chiron? Hello, Eddie. Hello, Jeff. Thank you for liking. Right now, the #1 top fan is Reese because he's modding. Then we have Speed Kills. Then we have Eddie. Then we have Steven Sky Reading. #5 is My Music. #6 is Jeff. Poor signal? Oh no, what's a poor signal? I'm from third. Oh, Big Kahun is saying you're from Yemen. Welcome to Yemen. Hello, Space Fright. Thank you, J-Dub. J-Dub417 has done a super chat. Thank you. Can we get 20 likes? I'm so sorry. I hope you feel better. Okay, I'm gonna sip some water and then we will get on to the reading and keep on discussing, okay? Tyson, you're here. Hi Tyson. Thank you so much. Thank you for liking the live. We're gonna do black holes and then we're gonna do the Big Bang like we planned, okay? All right, let me take a sip of water and then we will be doing that, okay? Okay. Scott, are you here? I know. I was interrupted by a Martian at my last live. I don't like that at all. I don't. I don't like it. Sometimes YouTube does have glitches and it just kind of ends the live. I don't like it. Okay. Let me really quickly set it up. We will be reading from Death by Black Hole by Neil deGrasse Tyson. We did a spiel on black holes and stellar remnants and planets in the previous live just now. Hello, Awesome Sauce. Thank you. Hey, gorgeous. I hope you have a wonderful day. I'm proud of you. Thank you. I did not get all A's in high school. My high school was in India, so no. Absolutely not. I did get all A's in calculus and math in college, though. I don't think I've gotten a B in a math class, but I've gotten a B in physics. I need to get a, yeah, I need my super chat goal, guys. I do. I do. I do. Let me tag the book. Can we get 30 likes? I love that. I love that. We had a pretty natural discussion just now in the last live, but it got interrupted. Okay. I tagged some books. Thank you for the super chat, everybody, and gifts. Nope, the heart didn't work. J. Manuel! Thank you, J. Manuel, for the party hat. I only caught it at the end. Hi, Azam. All right, let's finish up the black holes part from last night, okay? So last night we talked about, I have seen a shooting star, yes. Last night we talked about black holes in some detail. So if you want to catch the full black holes live, you should go and look at that from last night. We went live and we discussed that. Tonight we will continue and finish that up, and then we will go on to another topic, okay? So this is Neil deGrasse Tyson, Death by Black Hole, and we're on the chapter called Death by Black Hole. This book has lots of chapters, and we're currently on this one. Finishing up, okay? Whenever a theoretical astrophysicist needs an energy source in a tiny space to explain a phenomenon, well-fed black holes become prime ammunition. So last night's live was called Hungry Black Holes, and if you check it out, you'll see why we called it a Hungry Black Holes. So that's what's going on continuing tonight. For example, as we saw earlier, the distant and mysterious quasars wield hundreds or thousands of times the luminosity of the entire Milky Way galaxy. A quasar is an active galaxy example. So we have also talked about various types of galaxies. A quasar comes from the word quasi-stellar or quasi-star or star-like. People, when they first saw quasars, thought that this was a star, but turns out that they're actually a very unique type of galaxy with a very active galactic nucleus, or a very sort of explosive and active active galactic nucleus. And the interesting thing, what stands out about these quasars, is that the galactic centers outshine the rest of the galaxy. So bright is their center. It is sort of dominating the luminosity of that galaxy so much that from a very far distance, they look like a star, like a point source of light. So, but turns out that they're actually a whole galaxy. Okay, so that's what a quasar is. And a quasar too will have a supermassive black hole at the center, eating a lot from its surrounding materials and things like that. Okay, so let's see what this has to say. For example, as we saw earlier, the distant and mysterious quasars wield hundreds or thousands of times the luminosity of the entire Milky Way galaxy. But their energy emanates primarily from a volume that is not much larger than our solar system. So it's an entire galaxy, but most of the luminosity comes from a much smaller part of that galaxy. So much so, like I was saying, it looked like a point source of light to us from a distance where we would think that it is kind of like a star. So they were quasi-star or quasi-star. But there were other things that were kind of confusing us, for example, the spectra and such, which made it seem like, or also the wavelengths emitting from these objects also were mysterious to us. So they were actually something confusing to us for a while, but then we realized that we found this new type of galaxy, okay? So their energy emanates primarily from a volume that is not much larger than our solar system. Without invoking a supermassive black hole as the quasar's central engine, we are at a loss to find an alternative explanation. So we think that basically there's a supermassive black hole at the center of this galaxy, which is doing a lot of activity. It's eating up from its surrounding materials, and there's just like massive accretion happening and lots of radiation coming from all those infalling material. And it's the type of galaxy where that is the main source of the luminosity for that galaxy. That stuff that's happening at the center of the galaxy is pretty much producing all of the, or most of the luminosity. And that is where it's kind of different from, say, the Milky Way galaxy. The Milky Way galaxy also has a supermassive black hole at the center, but our luminosity is not coming mainly from there. Sure, there's a lot of luminosity coming from that galactic center of our galaxy, but we also have a lot of stars. We're a more wholesome galaxy with lots of things producing the luminosity, lots of stars. But active galactic nucleus, or something like this quasar, is different, unique in the sense that most of the luminosity is coming from their center, okay? We now know that supermassive black holes are common in the cores of galaxies. So, I've lost my sentence. For some galaxies, a suspiciously high luminosity in a suspiciously small volume provides the needed smoking gun, but the actual luminosity depends heavily on whether stars and gas are available for the black hole to shear them apart. Other galaxies may have one too, in spite of an unremarkable central luminosity. These black holes may have already eaten all the surrounding stars and gas, leaving no evidence behind. So it really depends on what stage of the galaxy it is in when we're observing, which could show us sort of a lot of brightness coming from the center or less brightness or what have you, okay? But stars near the center in close orbit to the black hole, not too close to be consumed, but they're orbiting the black hole, will have sharply increased speeds. These speeds, when combined with the star's distance from the center of the galaxy, are a direct measure of the total mass contained within their orbits. Armed with these data, we can use the back of an envelope to calculate whether the attracting central mass is indeed concentrated enough to be a black hole. So this is how we're estimating sort of the mass that's within that orbit. The largest known black holes are typically 1 billion solar masses, such as what lurks within the Titanic elliptical galaxy M87, the largest in the Virgo cluster of galaxies. So in the Virgo cluster of galaxies, we have M87, and it has one of the largest black holes, at least at the time of writing, the largest known black holes. That one. Far down the list, but still rather large, is the 30 million solar mass black hole in the center of the Andromeda galaxy, our near neighbor in space. So apparently there's a 30 million solar mass black hole in the center of the Andromeda galaxy, another supermassive black hole example. Beginning to feel black hole envy? You are entirely justified. The one in the Milky Way's center checks in at a mere 4 million solar masses. So still millions of solar masses, but around 4 million solar masses is the Milky Way's center. But no matter the mass, death and destruction are their business. So that is the end of that chapter. I wanted to say a few more things. So basically, because we touched upon the topic of quasars really quickly in this chapter, again, I wanted to say a quasar is a galaxy. It's an example of active galaxies. We actually have a live stream on that as well. And a quasar also has a supermassive black hole. It's just one of the more extreme examples of a supermassive black hole eating so much material and causing this type of luminosity where most of the luminosity is coming from that galactic center of that galaxy, and far, far away, they look more like a star or a point-like source of light. But they have lots of other features that would be very confusing for a star to have. And so eventually people realized, oh my gosh, these are just really unique and different types of galaxies that we have chanced upon and whatnot. Okay, so that's about quasars. But actually, we also then kind of realized that a lot of galaxies have supermassive black holes at their centers. And these black holes, remember, I mentioned earlier that a black hole is a stellar remnant. Basically, a star dying sometimes, depending on the star's mass, the most massive stars can make a black hole, which comes from extreme gravitational collapse. But a supermassive black hole is one that has eaten, it's a hungry black hole that has eaten for many, many years, maybe billions of years, and has gotten bigger over time. So these supermassive black holes are not just like, just a regular black hole in that sense. They have eaten a lot, and they've eaten from their surrounding materials. And sometimes because they're eating and the surrounding materials are falling in, that accretion of the material surrounding the black hole itself can be very bright and giving off a lot of radiation, because this black hole is sort of this natural accelerator of those materials, particles, whatever, and that can produce a lot of radiation in various wavelengths, and maybe even particles, maybe even gravitational waves. We have a supermassive black hole at the center of our Milky Way galaxy. It is millions of suns in mass, around 4 million suns in mass. Other galaxies could have even more, could be billions of solar masses, could be many more millions of solar masses, things like that. So there's a sort of a diversity of these supermassive black holes as well. One thing to note about, for example, our galaxy versus a quasar is that our galaxy has the galactic center, it has lots of stars, it has sort of more active areas of the galaxy where there's basically birthplaces of new stars, a lot of gas, it has a halo. So our galaxy, in other words, I would consider a more wholesome galaxy with a lot of different things going on. And our galaxy's luminosity is not coming solely or mostly from that galactic center, which is pretty active even for our galaxy. But we have stars and lots of other sources like that producing the luminosity of our galaxy. For a quasar, the quasar center pretty much rivals the entire galaxy's luminosity. So that's where we're different. We're more a regular galaxy. We're a very beautiful galaxy because we have a spiral shape, whereas a quasar is called an active galaxy. Okay, so just wanted to kind of mention that as well while we're on the topic of black holes, because the black hole topic, remember, we had the general relativity conversation and how classically black holes were theorized, and then how that works, like the physics of black holes and whatnot. But then we also talked about the astronomy and observing black holes, and also then about the stellar remnant notion of the black holes. And then now we have also covered supermassive black holes. So with that, we're kind of done with this chapter from the book, and we'll keep on going. We'll move on to the next topic, but let me know if you have any questions. Hello, Mama Do Ali. Hi, Brad. Hello, Kale. So Risa asked, it's the supermassive black hole's event horizon that no. So the event horizon is the boundary between where light can escape the black hole versus if you keep going beyond into the black hole, then light cannot escape the black hole. Nothing can escape the black hole. Pretty much there are things that are orbiting the black hole. And if you get any closer, things will get accreted into the black hole. So we were just now talking about how even the stars that are orbiting the black hole can kind of give away the mass of the black hole and that there is a black hole, etc., because the star's velocity, etc., those things are important in our observations to kind of be able to say whether there's a black hole and how big it is and things like that. But basically, if you get much closer, if you get any closer than where the stars can orbit and not be eaten, then basically you start to also get gas clouds and stars that are being eaten by the black hole. Like at first, it will look like it's orbiting, but it will spiral into the black hole, and that whole spiraling into the black hole situation gives off a lot of radiation because all that matter that's falling into the black hole, those particles, everything's getting accelerated, and there are different ways in which there is radiation coming off of that material. Okay, so just imagine the material, the stars, the gas clouds, everything is undergoing the tidal forces of the black hole, and everything is getting accelerated by the black hole into this how should I put it, into this grand death, basically, because eventually the material will fall into the black hole and we won't be able to see it again, it won't come out, etc. But as it's falling in actively, it can give off a lot of bright radiation. As in, that material is falling in, it hasn't gone past the event horizon. Okay, so pretty much once you're crossing the event horizon of the black hole, after that, it's all darkness. You cannot see. So black holes are kind of hiding away in that sense, right? You can't really see the black hole, but you can see the stuff that's falling into the black hole until the point of the event horizon. Once the material falls in past the event horizon of the black hole, you cannot see it anymore. Okay? But there are stars that are safely orbiting the black hole, which we can see. And those stars' behavior and how fast they move, etc., can tell us something about the black hole. And then there's material that is not just orbiting, but dangerously falling into the black hole. And the fall is still happening. It's not that it's done eating those things, it's still falling, as in happening right now. So it's still present tensing, it's falling. And it's spiraling in it because it could be this ginormous, it could be huge gas clouds or huge stars getting ripped apart and spiraling into the black hole, undergoing the tidal forces and everything that we talked about last night. For even a human being, if anything that falls into the black hole that has sort of an extension would undergo these tidal forces. So it looks very, I guess, magnificent when the object that's falling in, all the spaghettification, exactly, all the spaghettification of the stars and gases that are falling into the black hole would look different in the sense that this is a lot more material. All that material falling in, particles getting accelerated, will give off a ton of radiation in multiple wavelengths, usually. It could be X-rays, could be UV rays, there could be particles getting ejected or something, and you could maybe see that. Depending on what you're looking with, what type of instruments you look at this thing with. But basically, that stuff can produce a lot of bright radiation in various wavelengths, which would give it away, that there is a black hole. That's actually how we just discovered Sagittarius A star, which is the supermassive black hole in our own galaxy. Sagittarius is the galactic center. That whole situation, our galactic center is Sagittarius, but Sagittarius A star with the asterisk there is the black hole. And after observing the galactic center of our own galaxy, we basically had to conclude that there is a black hole, and we got sort of an estimate for how big it is and what the radius is and what the mass is and everything like that. Because you're basically seeing it kind of indirectly, in the sense that you're seeing it through the behavior of the materials around it and also the radiation around it from the materials falling in. Okay? Thank you so much, everybody, for all your support and likes and shares and subscribes and questions. I really appreciate it. And can you please help me with my super chat goal? According to whom, on the basis of what? Says Bernard Doe. What are you talking about? Black holes are stellar foodies. Hi, Chicken on Biscuits. Oh my gosh, Chicken on Biscuits is here. Black holes are stellar foodies, but they're just foodies. They're stellar foodies. They're gas cloud foodies. They will feast on anything, depending on if you get close enough to be feasted on. They will pretty much suck you in, but not necessarily like a vacuum cleaner. The falling into the black hole doesn't have to be this clean dive that it just happens and no one sees it. It can be sort of that swirly, spirally fall that happens over time and produces a lot of bright radiation. Sort of a more of a magnificent fall. Okay. Thank you, Jim Manuel, for the Sunday. Thank you, Manuel. Thank you for the gifts, guys. Do white holes exist? Brad is asking. I'm not sure. Can you have a pocket black hole, like a really tiny one? Do they have to be big? That's a great question. Family-friendly galaxy. I like that comment, Scott. Hi, Mark Heldman. Thank you for the questions. I do have books. Hi, Beethoven. Hi, Joshua. I have books. I tagged a few in the live. Are you asking, do I have books that I wrote? I do. They're on Amazon. I have a review on gamma ray bursts on Amazon. If you search with my name, you can probably find it. Oindree is my first name. You can search it on Amazon. So let me answer the... Hi, Sarah. So Ryan Hawkins asked, black hole give off radiation waves, doesn't it? So it's the material giving off the radiation waves. The material that's falling into the black hole actively, that will give off radiation. So before the material passes through the event horizon of the black hole, because it's accelerating, the material gives off the radiation, okay? Which kind of illuminates the presence of a black hole there. So, sort of ironically, even the black hole is very dark. Around the black hole can be very bright because of its accretion of materials. If the black hole is a hungry one that's eating a lot, okay? Reese asks, so could black holes be what we call dark matter? We don't think so. There was a theory at one point, or an idea at one point, that maybe dark matter is just a bunch of compact objects that we can't see. But no, we don't think that black holes would really account for this phenomenon or this effect that we see, that we say is caused by dark matter. No. So you wouldn't be alone if you thought that. Basically, people did think of that. People did think that maybe compact objects, which would be kind of invisible, but we know that they exist because of their gravitational effects. Maybe that is the cause of dark matter. Maybe that is dark matter, but no. Unfortunately, that doesn't account for all the dark matter that we see. Okay? Let me go back to that question. What's the halo thing called around a black hole? Maybe like an accretion disk? There is a halo of our galaxy. It's the sort of galactic halo, if that's true. The black part is so called because the gravity is so strong that light cannot beat the escape velocity. Yeah. Light stays inside the event horizon of the black hole. So the past the event horizon, it's all dark. Ooh, Ryan had asked, can you have a pocket black hole? Like a really tiny one? Do they have to be big? No, they don't have to be big. You can have a pocket black hole. So, I mean, it would still have very strong gravitational field, so I wouldn't really recommend one, but it really depends on compression of some material, some massive object, could even be you. We can turn you into a black hole, Ryan. We would just have to compress you a lot. So classically speaking, a black hole is determined by its Schwarzschild radius. We can do the math where we simply set the radius of some massive object to its Schwarzschild radius, which is basically the math you get from setting the escape velocity of that thing to the speed of light in vacuum. And once you do that, you have a Schwarzschild radius, and that is the black hole radius, classically. And so pretty much anything with mass actually has a Schwarzschild radius and can potentially become a black hole. But is it practical? Not usually, and not easily, thankfully. So thankfully, most small objects would be impractical to turn them into black holes. So we don't. Something like a star, which has a lot of mass, it's a much, much more massive object, can have a natural gravitational collapse that compresses it enough to where it meets its black hole radius requirements on its own naturally. But for us to do it here on Earth with small things, that would be very challenging. But in theory, everybody, all of us, have a black hole radius. We can all be compressed, and anything mass can actually be compressed to become a black hole, but it is generally not practical, is why we don't have that. Okay? It's the other way around. Stars and suns can, well, depends on their mass, but they can become black holes. Black holes don't become stars or suns. No. The stars die to become a black hole, so there's no going back to a star. What happens at the event horizon? Well, up to the event horizon, you can have light come out. You can see, observe things. Once you cross the event horizon, that's where you've gone too far and you're not going to come back out, or light will not come back out. So like, say if you're falling in pretty much into a black hole, then okay. If you're falling into a black hole, and say some other people are seeing you do that, they can see up to the event horizon. They won't be able to see after that. So the event horizon is basically another way of setting the Schwarzschild. It's just a definition in space of the boundary between where light can escape and where light cannot escape. So yes, hello MD Parvez. You should help me with my super chat goal of tonight. Thank you so much, and thank you for your support. So let's see. Somebody asked, does a black hole ever stop existing, or does it die out? Yes. So a black hole, so now we're getting into some quantum mechanics. Due to the uncertainty principle and quantum mechanics, a black hole can actually have a temperature and can actually quantum mechanicsly emit some particles, some radiation, okay? And because of this, it is actually giving back to the universe in a way, and could eventually kind of go away. It loses its mass over time. Hello, Omni King. Hi, Divine Intelligent. What is your profession? I mind my own business. How about you, Omni King? You should be a professor. Thank you. Are you from Pakistan? I am not. Depending on how you define things, I suppose. Hello, Divine Intelligent. Hello, Mark. Quantum entanglement explains how I feel about you. Thank you, Aaron. You could share some of your own knowledge, Omni King, instead of being a DICK. Thank you, Ultra Superman. Thank you, MD Pervez. Thank you, Aaron. Thank you, Mark. Ooh, let's look at the top fans. Number 1 is J Manuel. That's because J Manuel did a gift. Thank you so much. Number 2 is J Dub. J Dub also did a gift. Thank you so much. Number 3 is My Music Gen X. Thank you, My Music, for all your support. Number 4 is Ryan Hawkins. Thank you, Ryan. Also, Ryan, I believe, is a member. So thank you so much, Ryan, for your membership and support. Really appreciate you, especially at these early stages of my channel. Appreciate your support. I understand I need to expand on the members only content, but because I'm still growing, it's taking a little bit of time. So appreciate your patience. Thank you so much. Number 5 is Aaron RLJ. Hello, Aaron. Number 6 is Mahmoud Ali O. Number 7 is Vplo CC. Hello, Vplo. Number 8 is J Franks. Hello, J Franks in Italy. Number 9 is Shaggy's Moving. Hello, Shaggy. Number 10 is Mark Heldman. Number 11 is Larry. Number 12 is Mr. Drew. Number 13 is Brad. Number 14 is Tyson Jays. Hello, Tyson. Thank you for modding. Thank you for your support as usual. Number 15 is Joshua. Hello, Joshua. If you have a question, let me know. You can also do a super chat to highlight the question if I missed it. Number 16 is Reese. Hello, Reese and Charlie. Number 17 is Kyron. Number 18 is Speed Kills. Number 19 is Slayum. And number 20 is Block Beethoven. Well, don't do that. I like Beethoven. How do you feel about string theory? Hello, Mr. Real Estate. Hello, Viper. Hello, Meep. How do I feel about string theory? So first I should mention that we have done lots of lives on string theory. We have read books on string theory as well on this channel, so you should definitely go find those lives from the past. My feelings on string theory is that it's too bad that it cannot be tested, and it's too bad and so sad that superstring theory is untestable. Because physics is an experimental science, I feel like it's going to be a little difficult for this candidate theory to be considered successful because it is not testable. Okay, but I appreciate the efforts of people who work on it. People do move on to different topics, but that doesn't mean that the, efforts were useless. Scott is asking, how am I not in the top 25? I'm so sorry, because remember how this live restarted? Like, I had to start a new live. In the last live, you were probably in the top 5 because I think you did a super chat there. But this is a new live. I know, it's so annoying because that live had a glitch and it just ended itself. I had to start a new one, and in this one, you are not in the top yet. Sorry, but you are in our hearts. Hello, Mark. So somebody said, Music Gen X said, string theory is so 2000. I mean, look, the thing is that it's not the case that string theory doesn't have any value, because whenever you do a deep scientific study, you are actually, and of course, once you like share it and publish it and peer review, like, put it out there, it does help. It does have value because it tells people what you've tried and what you were trying to do and what worked and what didn't. So there is a lot of value in doing the work, um, and trying and then failing, right? And then telling people exactly what happened there, because then those people won't try it and they know that you did, and whatever you did find, you can publish. And that's why it's so important to still publish, right? The problem is that it cannot be tested experimentally, and that really holds it back. The other thing is that just because people are working on other things doesn't mean that string theory is nothing. It just means that those other things might be funded and have more success. So sometimes people might kind of gravitate towards the types of physics or types of work that has funding, that has a future, that has sort of ways to grow and give us, results and things like that experimentally. And there's been a lot of focus on instrumentation and being able to measure things and being able to observe and improve our technology for observation. So string theory might just not be such a big focus anymore, but that does not mean that it didn't have value and the efforts were wrong or anything like that. Okay? You know me from somewhere? Where do you know me from? How do we know everything gets squashed inside? So, by the way, classical physics tells us that there is a singularity inside a black hole. There's this point of infinite density, blah, blah, blah. So there is the theory of black holes, which tells us certain things. But exactly what is inside a black hole, we cannot know because we don't have information coming out of a black hole. So the answer would be that we don't know what is exactly inside a black hole because there's no way to know, okay? Maybe there is a way to time travel once you get inside a black hole and whatnot, and we just won't know. So that's that. Certain things, as sort of intriguing or even annoying it might be, there are certain things that we cannot know because of the speed of light being finite, because of the laws of physics, and that's just how it is. Black holes can be rotating sometimes. Someone asked if black holes are static. Not necessarily. Black holes can have a rotation. It happens to the best of us? What do you mean? Scott. Thank you, Jakester. Thank you so much. Thank you for enjoying, or thank you that you enjoyed and sharing about that. I do typically have educational content. So I typically do educational content on physics, astronomy, cosmology, and did I say astronomy? Astrophysics. Pretty much the topics I cover are those topics: physics, astronomy, cosmology, and astrophysics. And those are also my background, what I did grad school in and everything like that. So typically, that's my content. We also present kitty cats and me hosting the lives and my content. But the most dominant content is the educational content. Yes. Please do subscribe. Mark Heldman is saying, I knew you a long time ago. Do tell. How do you know me? Isn't this moon cycle a wolf moon? I did hear about something with the wolf moon, I think in astrology. So I do astronomy. So I'm not, I hear about astrology though. Somebody did mention that there's a wolf moon, or I think there was. The last full moon was a wolf moon or something like that. Thank you, Jakester. I haven't started covering astrology yet, although I know some things about astrology just for fun. And cosmetology, sometimes I joke and say that I also cover cosmetology because I'll do like a lipstick ad. I mean, you gotta do what you gotta do to pay the bills, you know, and keep these lights on. So your super chat help, the gifts, and sometimes makeup and other things keep the lights on around here. So thank you for understanding. Which uni did you go to? I went to NC State University and Ohio State University. Let's hear about Big Bang. Okay, let's get that going. How do you prove gravity? Let me show you right now. See this? See how it felt? It followed a geodesic because of the gravitational field of this planet. This comb, it has mass. The Earth, it has mass. The Earth bends space-time in a way where this comb does this. There, gravity is proved. Every time I fall too, gravity is proven every day. Every day. All right. Wish my weight fell that fast. Okay. How much do I fall? Okay, so the next topic is called In the Beginning, from also the same book. I do play with gravity every day at the gym. So this book is called Death by Black Hole by Neil deGrasse Tyson. We will start to read another topic now. And let's see how that goes. Okay, it's called In the Beginning. Physics describes the behavior of matter, energy, space, and time, and the interplay among them in the universe. From what scientists have been able to determine, all biological and chemical phenomena are ruled by what those four characters in our cosmic drama do to one another. And so everything fundamental and familiar to us Earthlings begins with the laws of physics. In almost any area of scientific inquiry, but especially in physics, the frontier of discovery lies at the extremes of measurement. At the extremes of matter, such as the neighborhood of a black hole, you find gravity badly warping the surrounding space-time continuum. At the extremes of energy, you sustain thermonuclear fusion in the 10 million degree cores of stars, including our sun. And at every extreme imaginable, you get the outrageously hot, outrageously dense conditions that prevailed during the first few moments of the universe. So the first few moments of the universe were extremely hot and extremely dense. Daily life, we're happy to report, is wholly devoid of extreme physics. On a normal morning, you get out of bed, wander around the house, eat something, dash out the front door, and by day's end, your loved ones fully expect you to look no different from the way you did when you left and to return home in one piece. But imagine arriving at the office, walking into an overheated conference room for an important 10 a.m. meeting, and suddenly losing all your electrons, or worse yet, having every atom of your body fly apart. Or suppose you're sitting in your office trying to get some work done by the light of your desk lamp and somebody flicks on the overhead light, causing your body to bounce randomly from wall to wall until you're jack in the box out the window. Or what if you went to a sumo wrestling match after work and saw the two spherical gentlemen collide, disappear, then spontaneously become two beams of light? If those scenes played out daily, then modern physics wouldn't look so bizarre. Knowledge of its foundations would flow naturally from our life experience. And our loved ones probably would never let us go to work. Back in the early minutes of the universe, though, that stuff happened all the time. We're lucky that it doesn't happen anymore, but it used to be the case all the time. To envision it and understand it, one has no choice but to establish a new form of common sense, an altered intuition about how physical laws apply to extremes of temperature, density, and pressure. So basically, you want to develop a new kind of common sense, a new kind of intuition when we speak of the Big Bang and moments after the Big Bang. So now the Big Bang is the origin of the universe. We don't know exactly what happened at t equal to 0 of this universe, but moments afterwards, this universe was very small, very hot, very dense, and very different intuitive things were happening to the temperature, density, and pressure at that time. And we also sometimes call it the radiation-dominated universe. So we have now traveled back in time to a very different era of the universe when we speak of the beginning, or shortly after the beginning. It was a very different universe, not the universe that we know and love now, not the universe that nurtures us. No galaxies, there were no galaxies, there were no stars, there were no clusters, no galaxies, no stars, no people, no planets. But lots of photons, a very hot, dense, tiny universe, a baby universe. Okay? Albert Einstein first published a version of this famous equation, E equals mc squared, in 1905 in a seminal research paper titled On the Electrodynamics of Moving Bodies. So you can look that up and read it, by the way. It's by Albert. Better known as the special theory of relativity, the concepts advanced in that paper forever changed our notions of space and time. It gives us the relative nature of space and time, special theory of relativity, like we talked about earlier in the live. Einstein, then just 26 years old, offered further details about his tidy equation in a separate, remarkably short paper published later the same year. Does the inertia of a body depend on its energy content? To save you the effort of digging up the original article, designing an experiment and testing the theory, the answer is yes. As Einstein wrote, if a body gives off the energy E in the form of radiation, its mass diminishes by E over c squared. The mass of a body is a measure of its energy content. If the energy changes by E, the mass changes in the same sense. So that's E equals mc squared. Uncertain as to the truth of his statement, he then suggested it is not impossible that with bodies whose energy content is variable to a high degree, for example with radium salts, the theory may be successfully put to the test. So then, basically, a radioactive material, right, gives off some radiation, but is the mass of that thing decreasing accordingly? There you have it, the algebraic recipe for all occasions when you want to convert matter into energy or energy into matter. In those simple sentences, Einstein unwittingly gave astrophysicists a computational tool, E equals mc squared, that extends their reach from the universe as it is now all the way back to infinitesimal fractions of a second after its birth. The most familiar form of energy is the photon. It's a massless, irreducible particle of light. You are forever bathed in photons, from the sun, the moon, and the stars to your stove, your chandelier, and your nightlight. So why don't you experience E equals mc squared every day? The energy of visible light photons falls far below that of the least massive subatomic particles. There is nothing else those photons can become. And so they live happy, relatively uneventful lives. Want to see some action? Start hanging around gamma ray photons that have some real energy. I mean, don't do it. They're quite dangerous. But if you want to see some action, then don't depend on visible wavelength photons, but you might want to consider gamma ray photons, which have much smaller wavelength and much bigger frequency and much more energy. Okay? At least 200,000 times more than the energy of visible photons. You'll quickly get sick and die of cancer. Oh gosh, evil eye remove. But before that happens, you'll see pairs of electrons, one matter, the other antimatter. So by the way, if you want to see pairs of particle, antiparticle, this is one good way. Gamma rays will go into particle, antiparticle pairs, okay? They can go back and forth between the particle, antiparticle, and back to gamma ray and things like that. And that used to happen a lot at the beginning of the universe as well. So if you want to see electron-positron pairs, electron and its antimatter, this is the way to go. You may have to deal in gamma rays, okay? So you will see pairs of electrons, one matter and the other antimatter. One of many dynamic duos in the particle universe. So this is a dynamic duo, this electron-positron pair. They can go back and forth between electron-positron pair to a gamma ray and back to electron-positron and back to gamma ray. And this is the game that they played a lot in the early universe. Pop into existence. One of many dynamic duos in the particle universe pop into existence. You could see this popping into existence where photons once roamed. As you watch, you will also see matter-antimatter pairs of electrons collide, annihilating each other and creating gamma ray photons once again. So this whole situation of the gamma rays making electrons, positrons annihilating and making a gamma ray again, and back to the other, and back to this used to happen a lot. High energy, increase the light's energy by a factor of another 2,000, and you now have gamma rays with enough energy to turn susceptible people into the Hulk. But pairs of these photons now have enough energy to spontaneously create the more massive neutrons, protons, and their antimatter partners. So just like electrons, positrons, guess what? More energetic gamma rays, more energetic photons, and you get more energetic or more massive particles from that. So once again, let's read this. Pairs of these photons with more energy can now spontaneously create more massive particles such as neutrons, protons, and their antimatter partners. So neutron, anti-neutron, proton, antiproton, which neutrons and protons are, of course, made of quarks. And so those quarks will each have their anti-quark partner. So, not just electron-positron, the Big Bang, or shortly after, actually gave us a little bit of these protons and neutrons as well, which is what we speak of when we say that hydrogen and helium came from the Big Bang. Big Bang nucleosynthesis also gave us that, but smaller amounts. Electrons are not like photons, but electrons can come from photons in high energy situations. A photon, like a gamma ray photon, which is a very high energy photon, can make an electron and positron pair. That type of particle interaction is allowed, because particles can come from just energy. Okay? High energy photons don't hang out just anywhere, but the place need not be imaginary. For gamma rays, almost any environment hotter than a few billion degrees will do just fine. So there are many sources of gamma rays. In fact, there is a transient event called gamma ray bursts, which I have a review on Amazon, as well as my blog, which of course is a source of gamma rays. Okay, so gamma rays are quite normal, natural, can happen, and does happen in out in the wild in nature. The cosmological significance of particles and energy packets transmuting into each other is staggering. Currently, the temperature of our expanding universe, calculated from measurements of the microwave bath of light that pervades all of space, is a mere 2.73 degrees Kelvin. Like the photons of visible light, microwave photons are too cool to have any realistic ambitions to become a particle via E equals mc squared. In fact, there are no known particles they can spontaneously become. So pretty much, if you are a light particle, a photon with less energy, then you probably cannot make any particles, because particles too are associated with a certain level of energy. And that whole E equals mc squared way of making a particle with a mass is not going to happen if you don't have enough E energy. And more E comes from more frequency. Higher the frequency, the more energy. The more E, the more likely you could make a particle maybe. But pretty much, if you don't have enough E, no particles are being made. So microwave photons or visible light, those don't really make particles, or won't make a particle naturally. Gamma rays can do it. And depending on how energetic the gamma ray, it can even make more massive particles. Yesterday, however, the universe was a little bit smaller and a little bit hotter. The day before, it was smaller and hotter still, because the universe is expanding in the same direction as the forward direction of time. Roll the clocks backward some more, say 13.7 billion years, and you land squarely in the primordial soup of the Big Bang. A time when the temperature of the cosmos was high enough to be astrophysically interesting. So what was the situation in the primordial soup? It was very hot, very dense. So this type of thing happened all the time, like I was saying. The photons going into electron-positron pairs, maybe even some neutrons and other things. We will see. Can we get 100 likes, by the way? And can someone do a super chat so I can meet my goal? Thank you. The way space-time, matter, and energy behaved as the universe expanded and cooled from the beginning is one of the greatest stories ever told. But to explain what went on in that cosmic crucible, you must find a way to merge the four forces of nature into one, and find a way to reconcile two incompatible branches of physics. This exact incompatibility we have spoken about a lot on this channel in the past. What are these two branches of physics? Quantum mechanics on the one hand, physics of the small, and general relativity on the other hand, physics of the large. Okay? So there are two incompatible branches of physics. These two branches don't get along. And these are quantum mechanics and general relativity. Okay? And because of that motivation, we have also talked about superstring theory, which is a candidate for unifying them, except it's only a candidate because it cannot be tested. Okay? Spurred by the successful marriage of quantum mechanics and electromagnetism. So electromagnetism, on the other hand, has been married to quantum mechanics by the electroweak theory. So that also gave people hope that maybe unification is possible for all of the forces. So There was a successful marriage of quantum mechanics and electromagnetism in the mid-20th century. Physicists set off on a race to blend quantum mechanics and general relativity into a theory of quantum gravity. Although we haven't yet reached the finish line, we know exactly where the high hurdles are during the Planck era. That's the phase up to 10 to the minus 43 seconds. So the Planck era is the phase up to 10 to the minus 43 seconds. So when the universe was 10 to the minus 43 seconds old. Very, very tiny, very young, okay? After the beginning, which is t equal to 0. So from t equal to 0 to t equal to 10 to the minus 43 seconds is a mystery. And before the universe grew to 10 to the minus 35 meters across. So from t equal to 0, time equal to 0 to time equal to 10 to the minus 43 seconds, the universe grew to 10 to the minus 35 meters. So we call it the Planck era. Planck is known for being a number that is small. The German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited with being the father of quantum mechanics. So, as you can imagine, the universe was very quantum-like then. If we're considering things that are so small, 10 to the minus 43 seconds, time, 10 to the minus 35 meters, length, these are small. So the big was small then. So now we utilize general relativity to describe the universe and gravitation and things like that. But back then, the universe was tiny. So what do we use to describe it then? And can we agree? Can the different parts of physics agree? That is the question. The clash between gravity and quantum mechanics poses no practical problem for the contemporary universe. We do just fine with this clash, but the clash is a thing. We cannot ignore it if you get into the details of things. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems, and so they don't have to meet. But in the beginning, during the Planck era, the large was small. And there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony decided continue to elude us. And so no known laws of physics describe with any confidence the behavior of the universe during the brief interregnum. So during that time, if there was a marriage between the large and the small, we don't know the details of it. But you see how we still claim a lot of success at this point because this time period was only 10 to the minus 43 seconds. If we can say things with more confidence and a lot more confidence for after that brief period of time, then might just be good enough. Or at least better, right? At the end of the Planck era, however, gravity wriggled loose from the other still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged through 10 to the minus 35 seconds, it continued to expand and cool. So there's also that happening, expansion, which we call, we also don't know exactly why the expansion is happening. We say it's dark energy, and that is also a research topic. But because the universe expanded, it also cooled. Later still, the electroweak force split into, so by the way, because the universe expanded and cooled, that kind of split the electroweak and the strong nuclear forces, which were only unified under more extreme conditions. And later still, the electroweak force split into the electromagnetic force and the weak nuclear force when conditions became even less extreme with more expansion and more cooling. But gravity split away after that first Planck era, which is what makes things mysterious and difficult, even now, in understanding that first era, or about gravity being able to be unified or not, etc. Okay, so so the weak nuclear force, by the way, controls something like radioactive decay. The strong nuclear force binds the nucleus. The electromagnetic force binds, of course, molecules, and gravity binds bulk matter. By now, as in in the story, the universe was a mere trillionth of a second old. So now we're at trillionth of a second age of the universe, yet its transmogrified forces and other critical episodes had already imbued our universe with fundamental properties, each worthy of its own book. So the four fundamental forces split apart fully by the time the universe is only a trillionth of a second old. So not too old. And so you can see how we study those four things separately at this point. And there's a lot that goes into those studies of those forces, and we treat them kind of separate because conditions are so different, especially by now, where the universe has aged even more and things are even more different, and especially different from that first trillionth of a second. While the universe dragged on for its first trillionth of a second, the interplay of matter and energy was incessant. Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething ocean of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable their interactions. Even the photon is an example of a boson. None of these particle families is thought to be divisible, as in can further break down into anything smaller or more basic. Those are the fundamental particles: leptons, quarks, and bosons. Okay? Thank you for the super chat. I have a lot of books of Neil deGrasse. They're all from the library. Thank you, Joe Dirt. But I want more. I want more of all the authors who write science books. Okay. While the universe dragged on for its first trillionth of a second, the interplay of matter and energy was incessant. Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething ocean of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enabled their interactions. So all the bosons, there's a boson for each of the other families that enable the interactions. So for example, photon is the boson for electromagnetic interactions. The W and Z bosons are the bosons for the weak nuclear force. Gluons are the bosons for quarks. And quarks are what make up the protons and neutrons, okay? That's a little bit of particle physics for you in a nutshell. None of these particle families is thought to be. These are the fundamental particles. So we don't think that they are broken down further. Fundamental though they are, each comes in several species. The ordinary visible light photon is a member of the boson family. The leptons most familiar to the non-physicist are the electron and perhaps the neutrino. And the most familiar quarks are, well, there are no familiar quarks, except I just told you some quarks make up the protons and neutrons. So at least the protons and neutrons are familiar to us. We just have to know that they're actually composites of quarks. Each species has been assigned an abstract name that serves no real philosophical, philological, or pedagogical purpose except to distinguish it from the others. And so the quarks are called up, down, strange, charmed, top, and bottom. Bosons, by the way, are simply named after the Indian scientist Shotendranath Bose, who is, by the way, from the same city as me. The word lepton derives from the Greek leptos, meaning light or small. Quark, however, has a literary and far more imaginative origin. The physicist Murray Gell-Mann, whatever, who in 1964 proposed the existence of quarks and who at the time thought the quark family had only 3 members, drew the name from a characteristically elusive line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. One thing quarks do have going for them, all their names are simple, something chemists, biologists, and geologists seem incapable of achieving when naming their own stuff. I don't know why he went for that, but he did. Neil deGrasse. So, it's him, not me. Quarks are quirky beasts. Okay, whatever. Unlike protons, each with an electric charge of +1 and electrons with a negative charge of -1, quarks have fractional charges that come in thirds. And you'll never catch a quark all by itself. It will always be clutching onto other quarks nearby because of the strong nuclear force, which is very strong indeed. And I guess they're very codependent quarks. In fact, the force that keeps 2 or more of them together actually grows stronger the more you separate them, as if they were attached by some sort of subnuclear rubber band. Separate the quarks enough, the rubber band snaps, and the stored energy summons E equals mc squared to create a new quark at each end, leaving you back where you started. But during the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves in spite of being collectively bound to each other. The discovery of this state of matter, a kind of a quark soup, was reported for the first time in 2002 by a team of physicists at the Brookhaven National Laboratories. So even the quark stuff was different at that early stage of the universe. So more and more things that were so different back then. Okay, so really want you to kind of appreciate that moments after the Big Bang was a very different universe than what we see now. Can we get 100 likes? So let me take a little breather and read the comments. 1 second, please. I'm gonna put a marker on this. We will talk about this. We will definitely finish this Big Bang soup discussion at some point. But let me catch up with the comments really quickly. And then I might have to get a warm drink because I'm actually getting kind of cold. Can we get 100 likes, please? Are you Indian? Yes, I am from India. One Mad is asking. Excuse me, please. Can we get 90 likes? And then 100 likes. Billy is saying all of this intellect and still depressed. Hello, Crazy Sick Wine. Are you gonna do a super chat tonight, Crazy Sick Wine, to celebrate getting into med school? Hi, Jakester. Jakester is saying my brain just got bigger, thanks. Oh, yay! Did you subscribe? Of course. Did you know the tidal forces of the moon also creates tides within your body because we're mostly made of water? Makes sense. Enjoy your money and live alone, says I love blacks. Okay. Thank you for the hearts. And thank you for the likes, liking the live. Hello, Limat. Pregnant women often send high-value super chats. If you're pregnant, send a super chat to keep the streak alive. Oh, my music Gen X, you must have been here the other night when we had a pregnant guest. It was Grace, and I ate a sandwich in her honor. In fact, I think I ate multiple sandwiches in her honor, and we called it the pregnancy sandwich. Thank you so much, everybody. You're more interested in my Antarctica stories. Okay. What are your questions, my love? Hello, Mark. Lasagna. X Power X House. Hello. Has anyone told you your voice is very pleasant? They have, but thank you. I saw your face in a crowded place and I don't know what to do. You're beautiful. You're beautiful. It's true. When is it sandwich time? I think it's gonna be warm drink time really soon here. Thank you guys for all the comments. Oh my gosh. Let's look at the top fans. Number 1 is Joe Dirt. Thank you, Joe, for the super chat. Number 2 is J Manuel. Thank you, J Manuel, for the gifts. Number 3 is My Music Gen X. Thank you, My Music. Number 4 is Meep. Number 5 is Odalune. Number 6 is Scott Romer. Hello, Scott. Now you're showing up in the top 10. Number 7 is J-Dub. Number 8 is Brad. Number 9 is Slayum. Number 10 is Mark Heldman, who I believe has been saying that he knows me, but won't tell me how he knows me. How do I know you? Were we in school together? Are you just making that up? Venetian days? Venusian? Do you mean Venusian? Venusian lifestyle? Spacetime is asking, hi Andre, what time is it in Boston? It's 3:22 in the morning. Let me turn on the heat from my other phone. You're beautiful. He knows me from my Venusian lifestyle. Hello, Salty. We almost are close to having 100 likes. Let's get there. Mark Heldman. And you said, I know you from where again? Can you say it again? So you also don't remember. And you're asking me to remember? I did take a shower tonight, Felipe. I know. I've been going live quite regularly. For you guys. For you guys. For you guys. Mwah. For you guys. And my love for physics. For you guys and my love for physics. Mwah. Oh, that's right. I'm also a passenger princess. I'm a passenger princess. ¿Cómo estás? I know, where is college level? My mod. One of my mods that is extremely good at their job. Crazy Sick Wine, how is it going with your school situation now? Have you given all your money to John Hopkins, or do you have some left over for our super chats tonight? I thought you were gonna ask me to explain something harder than that. JK, JK. Don't be ridiculous, darling. Hello, guys. Thank you so much. Welcome. Come on in. Please do like, share, and subscribe. We want to get to 7,000 subscribers, please. Thank you so much. Thank you so much. Please do rewind if you want to catch the full discussion. We've been talking about some physics. I talked about black holes as well as Big Bang and shortly after the Big Bang and other things. So please do subscribe, like, share, tell your friends, tell your brothers, tell your lovers, tell your sisters. I need to get a PO box. Should I eat some carrots with dip? I think I'll do that. And then I will make my Horlicks warm drink. I already ate my PB&Js for the day today. I already had my PB&J. So 5 a.m. What do you mean? It's not 5 a.m. It's 3:29 a.m. Elijah, don't be a party pooper. Don't be. Don't do it. I have to be here until my goal is met. I just have to. Be right back. Fuji Papu. Oh my Fuji, do you want to go to bed, Fuji? Oh Fuji. Oh Fuji, Mama loves you. Fuji. Do you have a hairball, Fuji? Do you have a hairball? Okay, Fuji, Mama will give you a green cheese. Come, Fuji. Fuji heard me taking out the cream cheese, and he's like, I need some. Here you go. Fuji, you're so cute. Mama loves you, Fuji. We're gonna eat some carrots now. We will. My goal is a super chat goal. Hi, Fuji. Oh, Fuji. Mama loves you. They're all here. My what? Blue sleepers? What are you talking about? Hello, Tennessee. This is cream cheese. We always end the stream with some eating. Let's say goodnight, guys. you, J. Manuel. I wish I had chips. Thank you, J. Manuel. You're so kind. You have very nice teeth. Are you rich? I spat out a carrot. You're funny. Thank you for liking. Can we get 100 likes? Hi, baby. Alright, I'm gonna do it, baby. Ocasio! I missed you, Ocasio. My live was interrupted, the earlier one. Ocasio, how are you? Thank you for the 100 likes. Please do like, share, and subscribe. Did you go to my other live? Did you go to my other live, Acacio? The one that got interrupted? You're so hurt. You're worried. Muchas gracias, Acacio. I've been on this live. You can rewind this one and watch it. We covered a lot of materials. We finished up black holes and then talked about the Big Bang. Thank you, Casio. Alright. You should eat, Mark. Good night. Good night, guys. Mwah. 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 See you tomorrow night, okay? Bye-bye. Good night.